Now we want to move on to talk specifically about the solubility of gases. So there's a common description of gases that you can find that they are not very soluble in water. So under ambient conditions, in a liter of water, you can dissolve 8 milligrams of oxygen. So that is true that oxygen has very low solubility. You can get some to dissolve, but that limit is really low. So generally, we would kind of tend to say oxygen is not soluble in water because that's barely any dissolved in water. But this in general is not true that gases are not soluble in water. If we look at, for example, HCl, hydrogen chloride, that's a gas at room temperature, and you can dissolve 720 grams of it in 1 liter of water. So you can dissolve a ton of this. It's still a gas at room temperature, meaning that's not the right trick to use. Instead, we should still rely on polarity to predict solubility. Gases, things that are gases at room temperature, have weak intermolecular forces. Right? That's because their boiling point is below like 20 degrees Celsius. So they have pretty low boiling points, meaning they probably have weak intermolecular forces. So a lot of gases are just nonpolar molecules. Most gases are nonpolar. Nonpolar compounds are not soluble in water. So we do not want to use the rule that gases are not soluble in water. That is not true. Small gases, very small polar things like HCl, still are gases at room temperature, but they're extremely soluble in water. So the rule should instead just be, is the molecule polar or nonpolar? And polar gases, really soluble in water. Nonpolar gases, not very soluble in water. Very low solubility. And so O2 is a stereotypical case. There's really very little O2 that is dissolved in water. And so one of the things that makes gases unique, though, is that their solubility not only changes with temperature, but also pressure. So we saw previously that we can vary the solubility based on conditions. And with gases, the pressure of gas above the liquid explicitly affects solubility. So the first one, temperature. Solubility of gases decreases with temperature. What that means is when you increase the temperature of, say, the liquid that you're trying, or the liquid that you're trying to dissolve your gas in, less of the gas dissolves. And we can understand this as being based upon increasing speed, in much the same way that liquids tend to boil or get higher vapor pressures when they go to higher temperature. Less of the gas molecules are going to be in the liquid because the liquid's hotter. All the molecules are moving faster. If the gas molecules are moving faster, they're bouncing around real fast out here. It's unlikely that they would collide with the surface of the liquid and get stuck. The solubility of gases is going to be the same idea. They have to have an attractive intermolecular interaction with molecules that are in that solvent liquid. If everything's moving fast, you have less intermolecular forces, less or weaker intermolecular forces. The gas molecules don't stay dissolved. They pop right out. So the one implication of this is if you've ever had like a carbonated soda in your car in the summer here, it gets quite warm. You have a bunch of dissolved gas inside that carbonated liquid. It all is going to become undissolved, and it forms a pocket of gas that then can cause the can to rupture. It can cause it to explode, and you can get that drastic release of soda all over the place. So that's why you shouldn't store carbonated beverages in your vehicle in the summer. Really any time of year, but definitely during the summer. The other thing that drives solubility of gases is pressure. Higher pressure leads to much higher solubility of gases. And one of the reasons we can think about that is pressure is characteristic of the collisions of gas molecules with their container, right? It's the force of those molecules colliding with the container. Well, one of the sides of the container is the surface of the liquid. So higher pressure means more collisions with the surface. The molecules are just hitting the surface of the liquid more frequently. What that drives is just more introduction of gas molecules into the liquid. More of them will dissolve. So this is how carbon dioxide gets dissolved, for example, in Coke, right? Because they bottle it or they can it under really high pressures, say 6, 7, 8 times the pressure in normal atmospheric pressure, getting a lot of carbon dioxide to now dissolve into the solution. That is why you get a drastic release of all that dissolved carbon when you break it open. Inside that can or that bottle before you open it, the pressure is like 8 atmospheres. When you open it, all of a sudden it goes to whatever the pressure is of the air, and you get a release of all of that carbon dioxide. The bubbles that are forming is going from being dissolved to being heterogeneous. They're no longer dissolved. They collect together in bubbles and then they leave. They come out of the liquid. Instead of a solid that collects at the bottom, they just escape out the top. And so that's why you have that release. When you shake it up, you can increase some of the pressure of gases, and then you get a much more violent and a much more quick release of all of that gas from being dissolved to being not dissolved, and that's why you get it to come out really quickly. When we want to predict gas solubility with pressure, it's proportional. So Henry's law is an equation that tells us the solubility of gases is equal to some constant multiplied by the pressure. So if we want to increase the pressure, especially for relatively pressures close to ambient pressure or relatively lower pressures, that as you increase the pressure, say if you double the pressure, you would double the amount of dissolved gas. And so this allows us to make predictions as to how we want to get the, if you want to get a certain amount of gas dissolved, say carbon dioxide in your soda, you can get more or less based on the pressure. So the pressure is just that ambient condition you control. This KH then is a constant. That's just a number that is true for each gas-liquid pair. So for, say, water and oxygen, water and nitrogen, water and carbon dioxide at each temperature. So you need to look, though these are tabulated for a couple of temperatures, mostly 0 Celsius, room temperature, and maybe 100 Celsius. But you could define it for any temperature you wanted, what that sort of pairing would be. And so you'd have to look it up, but you could use this. It's just an algebraic expression. What we want to focus in on is kind of some of the ideas that this implies. So one of the things we can see is that, again, as you increase pressure, so as you increase the pressure, you can see that the solubility, the total amount of dissolved gas, increases linearly. So these are straight lines. These are only true for relatively lower pressures. If you get up to like 50 atmospheres, it's a different situation. But you can see it's different for each curve. So for helium, so we can see that's really flat. That means it's really hard to get helium to dissolve in water, whereas O2, you can get more of it to dissolve in water, and with increasing the pressure. And if you remember, increasing the pressure just increased the number of collisions of that gas with the surface. So the reason why we can understand why more oxygen gets dissolved is because it's a bigger molecule. All of these are nonpolar, but oxygen has the most electrons. What that means is it has the strongest dispersion interactions, so it has the strongest intermolecular forces when those oxygen molecules do get into water. So it's more likely that they will get trapped and dissolved into water. It has stronger interactions, and so they do go in. Helium, it's really nonpolar. It has 4 electrons. It's just an atom, so it's nonpolar, and has 4 electrons, very weak dispersion. It's really hard to get helium to dissolve in water. And the bigger the nonpolar molecule, the easier and easier it is to get it to dissolve in water as you increase pressure. You'll note at low pressures, they all have really low solubilities. But as you increase the pressure, you can get more of O2. That's why, and CO2 is an even bigger molecule. That's why they use it in soda. It's one of the bigger gas molecules. It has pretty decent dispersion interactions with water. So its curve would look something like this, where even more of it can dissolve. It's not that sharp, or that steep, but even more of it does dissolve at low pressures. If you bottled, that's why you don't bottle with air, because it's mostly nitrogen, so it'd be more expensive. Soda companies would have to use higher pressures. We can also see the effect of temperature. T1 is our highest temperature, and T4 is the lowest temperature. And so we can see that at those high temperatures, T1, it's again really hard to get the molecules to dissolve, because we know at high temperatures you have lower solubility. Because those molecules are moving faster, you have weaker intermolecular forces. You can't get these gas molecules to dissolve into the water. They just stay out. When they hit the surface, sure, there are more collisions, but they're moving so fast because it's a higher temperature, they don't get stuck and they don't dissolve. So it's a lot of the same ideas we had about vapor pressure. A lot of the same ideas, because physically it's the same thing. It's molecules colliding with a surface. And the question is, with the surface of a liquid, do those gas molecules get stuck? Do they stay in the liquid? Do they dissolve? That's it. 4 questions on participation 123. You want to find all 4 of them, get them answered, get those answers submitted over on Blackboard by Friday night. Week 2 homework due Saturday, covering both sets of videos, the end of chapter 10 and then the start of chapter 11. Post lab for evaporation and intermolecular forces is due Sunday. As a reminder, there will be the answers to the participation questions that will show up Friday night. That will be the only other video for this week. And there are answers to the post lab that show up Sunday night after that due date. You can see the ones for the first week. If you have any questions about anything, don't hesitate to email bdunnington@lee.edu. There's the question answer discussion board for stuff that can be more, kind of drawn out and other people can answer. You can also answer questions in there. If you have any questions about anything, let me know. Otherwise, enjoy your weekend. Check out the participation solutions video. Bye-bye.